Okay. Hi, everybody, and thank you for the very kind invitation, Giovanni, and all the organizing committee. Today, I would like to discuss with you Pocketron, which is the tool we developed to track pockets along time molecular dynamics, and also discuss a little bit on the complexity of allostery when you want to define it and understand it, let's say, mathematically. So our starting point is that we would like to understand it, allostery, from molecular dynamics. So I will discuss a little bit what molecular dynamics is, which is, I think, beneficial for some of the audience, and which is our strategy. Our strategy is built around the concept of pocket. That is, we track them, we detect them, we study them, and around them we build our networks, which we try to infer these allosteric communications. We have a component, which is a software, which is called Nxera, which is to define pockets statically from PDB structures. And also we track them a long time and trying to define these dynamical networks. Also, we discuss a little bit of kind of a large scale application of Pocketron on kinesis. The point is that now we have plenty of computational power. Okay, so we can start reasoning not just in terms of my system, I track it and try to understand my allosteric communication patterns, but we can try to go slightly beyond it. Is we have an entire family of structures, and we try to study them as a family, not just as one single structure, and try to see what is consistent in this family of proteins, statistically significant. I will discuss also a little bit on other strategies, because when you define it computation, we try to capture the computation is rather complex. So there are many ways, several mathematical tools that can be used to track this allosteric phenomena, and also some possible future developments. So why is complex allostery from the modeling perspective? Because at least for these reasons, it is a complex phenomenon, and to some extent is kind of elusive. First of all, it has a mechanical nature. Why I say that? It has a mechanical nature because when you model a protein, at least in the molecular mechanics approximation, what you're doing is to build this protein in the simulation like a set of atoms connected eventually by springs, okay, which oscillate. So it is mostly an harmonic system. So it is eventually a mechanical system, at least in the short range. In the long range, you have electrostatics. Okay, so any interesting phenomenon in biology is, I mean, mostly at least is ruled by electrostatic because it's long range, and its long range nature actually can shape many interesting phenomena. You just think to DNA, which creates this electrostatic cage kind of to protect itself. When you talk about allostery or any protein, let's say around phenomena, you're talking about free energy. So you're talking about equilibrium, also kinetics, but a very important aspect is about equilibrium. When you talk about thermodynamic equilibrium, we talk about potential and entropy. Okay, so you're talking about free energy, so you're talking about probabilities. So when you want to model a phenomenon, any kind of phenomenon, and also allostery, then you have to think that you're talking about statistical mechanics, which is the main tool which can help you in the mapping and understanding this phenomenon. So you have this, let's say, interplay between short range and long range phenomena, this oscillation short range phenomena, and this long range electrostatic phenomena. And also, as always happens in biological system, it is kind of environment dependent. Obviously, depending on the environment where your protein is, then you can have different mechanisms, different communication mechanisms, and so different effects. So the starting tool is molecular dynamics. Molecular dynamics, as a little bit anticipated, is the tool that we're using to try to model allostery and in general this communication phenomena in proteins. And this is particularly, I think, important for young people. Remember that what you see in a simulation cannot be more than what the theory allows you to see. That is, you have a force field with some prescription, with some, parameters which can allow you to see some phenomena, but other maybe more complex, more. So if you have molecular mechanics, you cannot see very well dispersion or things like that. And so one of the main tools you have here is the potential. Okay, the potential fluid, and then you have the integration of the equation of motions. Okay, with a stochastic term which accounts for temperature. So this is the framework in which you are, and this is where you can try to see something interesting about your system. And obviously, you have the proteins, you have it inside a box of water molecules. This is the environment in which you are playing your game. So, which is our strategy? As I said, it is built around the concept of pocket, okay, and it is. The main idea is to have these MD simulations long enough. Long enough is always complex in biology, but now we have kind of plenty of computer power, so we can go through microseconds to track them. Then we have this static pocket detection tool, which is used at every frame. So imagine you build your molecular movie, maybe with an access sampling, not an access sampling, by trying to trigger some events or not. And then once you have each frame, you get all the pockets. I will show you in a while how we do that. And then after that, we try to devise networks of pockets. So a static tool plus a dynamical strategy to track them a long time, including appearance, disappearance, annihilation, merging, a split of pockets a long time. So the first tool that we developed to do that is so-called, this tool is called NanoShaper. This is something which I coded several years ago now. And the idea of NanoShaper is that you deliver a PDB, okay, which you have also the parameterization of the radii together with the positions, and it's able to triangulate the surface, okay? So the very basic activity of NanoShaper at the very beginning was to build this molecular surface, particularly the solvent excluded surface, which is obtained by simulating the rolling of a probe, let's say a ball over the surface. And this can be used, for instance, to create a mesh of such surface, and then on top of it, you can solve, for instance, the Boston-Boltzmann equation, and you can get electrostatic around the protein. However, here, and this is something which is open source, it's fully available, you can download it, and it's Docker available too, so it's super usable on Linux. And you can use it, not so visible, but you can use it also via PMD. So you can open UMD, ask for the NanoShaper representation, you will get the molecular surface. But NanoShaper here is actually used first to get the pocket. Okay, not really to compute the molecular surface per se, just to make it visible. And the idea, the definition of pocket in NanoShaper, the static pocket definition that we have in NanoShaper is that a pocket is something which is accessible by water. It is not accessible by bigger probe. Okay, so as I mentioned, when we do computation in NanoShaper, we simulate the rolling of a probe along the surface. And in order to detect pockets, what we do is to do twice this activity. So we have here a small, okay, so this, let's say, pocket is closed by the rolling of the water molecule. And then we use another probe, a much bigger one, for instance, 3 angstrom, which is the default radius that we use for this virtual rolling probe. And what we obtain is this part here in black, which is the interior, let's say, of the surface. So this is our definition of pocket. It is 2 rolling probes, and then the volumetric difference between the 2 maps give us the pocket. And playing around with the size of the big probe, by modulating it, what you can do is to detect shallow pockets, okay, if you use a very big probe, or let's say classical traditional buried pockets by using a regular probe of 3 angstrom. Just to give you some numbers, it's relatively fast software, I think, because you can take, in a quite old processor now, I think, you can get in 7 minutes all 500 pockets on a virus surface. Okay, if you use it on a more normal, let's say, protein for instance, Abelson kinase, you can make it in 4 seconds. Actually, we are now working on the software to make it faster, so probably 7 minutes will became something like 1 minute, most probably in the next couple of months. So now we have the problem of switching from static to dynamic. So how we can move from a static definition of pocket on stack, which is dynamic, such that we can try to build these dynamical networks. So the basic idea is to cast the problem, let's say, of pocket tracking from tracking the pocket into tracking the residue which are around the pocket. Okay, so imagine you have your frame, you have several pockets arising, and you have the residues which characterize that pocket which are around. And then the problem is that you have another frame, another time step in your molecular dynamics, and then you have another pocket here and another pocket here, and then you want to try to understand who is who. So this is the problem that you want to solve. And if you cast the problem to residues, to atoms, this becomes rather easy, because it becomes a set, let's say, theoretic problem, let me say, in which you just say that in the end, by the Jaccard index, that is the intersection divided by the union, then you can immediately recognize if what you are seeing here is what you are seeing in the next frame. So you just compute the value of the overimposition, a Jaccard overimposition between the residues. And then if you get something different from 0, then it means that this guy is this guy, and that's it. If you have 0 everywhere, this is your Jaccard index is 0 with respect to all the pockets collected so far, the result is that this is a new pocket. So the overall result of this is that you have appearance and annihilation of pocket, and by this simple rule, you can track the fact that they are created and they disappear. So technically, let's say, by 2 matrices, you can solve all these problems, actually. So you have pocket at this moment versus the pocket stored so far, and you have pocket at time step t versus the pockets at time step t minus delta t. So this, from these matrices, you can track all the events of your molecular dynamics trajectory. And this is probably the most relevant thing to this venue, that is how we can try to give a definition of allostery by this tool, okay, by this strategy. Well, the definition we gave is that you have 2 pockets, okay? You have 2 pockets that get detected, and as I said, they are characterized by these surrounding atoms, surrounding residues. And our definition of communication, okay, that we gave is that when these residues are able to move from one pocket to another, so you have a pocket here, another pocket here, and they let's say surround first a pocket, and then in another step they surround another pocket. It means that these 2 pockets have a kind of, let's say, certain degree of flexibility. So it means that they share the residues, okay? The rate at which they share these residues gives you an information of local flexibility, okay? So this is the definition we gave of communication, and this allows you to build these communication networks inside your proteins. So long story short, this tool, Pocketron, allows you to track the pockets, all the events, the creation and annihilation. It is invariant to rotor translation by construction, so you don't need to align your trajectory because everything is related to residues. You can track volumes and surfaces. So as you can give an ID to a pocket, then you can track the volume along the time, then you can track the surface area along the time. The same pocket, you can see when it disappears, when it appears again, and so on. And so you can estimate the probability of existence of a pocket log time, which is rather interesting, because if it is cryptic and so cryptic not to exist so much, then maybe it's not that interesting for drug discovery. But if it is cryptic and kind of existing at least a bit of time, then probably chances are you want to spend time on it. And you can track all these split and merge events and among pockets. To give you an example of on what we applied the methodology, an instance, this is purine nucleoside phosphorylase. This is a system we studied a bit at this stage, and it is a homotrimer. You have 3 allosteric binding sites, and here there is a so-called 1/3 hypothesis, which means that you inhibit just one side and then automatically all the others by allosteric communication. The system, let's say, shut down completely. And indeed here we found that we can obviously track the allosteric sites, the 3 allosteric sites. They have high persistency. Then we can get also this kind of hub information, which seems that the 3 allosteric pockets communicate each other, let's say, So this is an example of the kind of analysis you can do. Here, actually, we did plain molecular dynamics, but you can do more than plain molecular dynamics. That is, you can use enhanced sampling to try to accelerate events and see what happens. And for instance, here you have an example on the A2A, applied to A2A. And here, for instance, we were able to see this kind of merge events of pockets. So you have two pockets which are distinct at this stage, then you have another frame in which they get together, then you have a peak of the volume, and then they split again. Other things that you can track here is the persistency level of the single residues, that is, which is not just the probability of the pocket itself, but the probability that that residue contributes to the definition of the pocket. Because obviously these objects, this pocket, move in time. So they are flexible. So it's not just that a pocket is fully defined by a set of residues only. So you have a varying definition of the residues along time. And this is also an information that you can track and say, okay, this pocket is 30% of the time, at least 30% of the time, these residues can be found in my pocket because they are flexible objects. Probably one of the most challenging things that we found is the Abelson kinase case, in which we started from say the wild type, then we simulated the variant, and then we found that according to literature, this communication network is interrupted. And then if you place myristate in this non-allosteric pocket, what you get is that the communication network is restored. And this is perfectly coherent with the experimental finding. So by this network, you can really have an idea, which is the path of communications between pockets. And you can see, I'm not talking a direct communication, not really direct link, but links which are mediated by the pockets that you find in your structure. They like it somehow, and this was highlighted when we published the manuscript. So kind of it was named Protein Games of Telephone, which is kind of funny because you have all this communication networking into the protein. So as I mentioned at the beginning, we have such a tool that can be applied to a protein. We're not applying systematically to an entire family, okay, of proteins. We have enough computational power. We have supercomputing centers. We have GPUs. We have everything in place to try to start in thinking not about one system, but about a family, okay? And so we are fortunate because MD is trivially parallel. So it's a very powerful algorithm with respect to system. Also, obviously, you can run all these things in parallel, and you can run plain MD for 3 microseconds and still get something, even without enhanced sampling, which starts to be quite meaningful. And then once you have this atlas of pockets we build, you can actually try to understand what is in common between this nectar and all these pockets. So don't study Allostery in one system, try to study an entire family. And what we obtain here, here it was the entire kinome of tyrosine kinome, okay? It took 1 year of computations in Cineca, which is still a lot, but it was fun. And not for the software power probably, but so what we found here is that we tried to use hypothesis testing on, let's say, on the probability of observing connections related to some specific pocket into the kinases. So in kinases we know, I mean, let me say almost everything. So we have the map of allosteric pockets. We know many things. So it's a very nice test bed in which you can try to see what happens here. And then you have your pockets, and then you know which are the allosteric one. And what you can do is to build this probability plot on the propensity, on the average propensity, this distribution in this case, of creating connection of each pocket. Okay, and here one of the aim was, the main aim actually was to compare active with inactive pocket and see which was the difference, and to check if by hypothesis testing we could see different communication patterns which are on average true. And another thing that we found, which is not strictly related to Allostery, is that by applying machine learning algorithm on all the frames on the trajectory, trying to predict which is the say activeness propensity of each frame, then we were able also to kind of in a minimalistic way, let's say it admittedly, but we were able to find that there is a this residue at DFG position +3, which actually from the fluctuations, on average, you can, by just looking at this one, this discovered in a biased way, let's say, you can conclude on the activity of the kinase, just looking at it with a probability of 82% of accuracy, which is not perfect. But the point is that we did that in a very unbiased way, let me say. So regarding the allosteric puzzle, I'm not here to say you that with Pocketron you will get all the allosteric communication fits, probably not. And the point is that because it is complex. So there are many possible definitions. There is just obviously not the one from Pocketron, but also, for instance, the one in terms of fluctuations. Fluctuations are very important when you try to detect allostery, because obviously you have this, let's say, common variation, okay, along time. You're measuring actually in an ensemble at the variance of your fluctuation with respect to the average value of the distance. So it's another way to look at the allostery and try to see, let's say, things that go together, let's say, in a synchronous way. But there are also generalized way to look at, let's say, correlation, like using the mutual information, which was done here. And so starting from the pockets that you have in Pocketron, you have this atlas of pockets in your trajectory. You can build these correlation matrices, and there use different definitions of correlations to try to see which are the difference, because it's a complex phenomenon. Maybe one definition only of correlation is not enough. We did that with several systems, and in the end, what we first check is that convergence. So convergence is always the problem when you do molecular dynamics. So which is the method which converge fast, which is the fastest method to converge to give you an answer on the stability of these connectivity matrices. And we found that DINET, which is based on the mutual information, was able to converge in 1 microsecond, whereas this distant flotation Pocketron actually requires a little bit more time. That is 2.5 microseconds to get something which is time stable that allows you to conclude. And also Pocketron consider that is affected by the fact that it is the tool that we use to track all the pockets a long time. So, I mean, also here it's included the time to track also pockets which appear, let's say, at the end of the simulation. So this is kind of beyond the natural thing itself. So the conclusions is that there is kind of an orthogonal behavior of these tools. They don't track actually the same thing. And Pocketron and DINET tend to be kind of rather conservative in giving information. Distant filtration instead tends to give, let's say, more filtration, particularly on higher distance, because one uses the threshold and the very near residue to avoid the trivial correlation on an alpha helix, for instance. And so they're two different aims, and then when you map to a non-allosteric things, they both capture allostery, but differently. And so the conclusion is that you have tools for concerted motions, like the flotation thing. Instead, Pocketron DINET seems more happy, let's say, not necessarily concerted motions, but actually, let's say, chains of communication, which is inherently asynchronous. So you have synchronous communication against asynchronous communication that goes over time. So if you want to use all these two together, so for instance, you can imagine that you have these two main paths. Let's say you go for MD, so let's look at below. So you go for MD, and then you do your Pocketron analysis or something like that, and then you try to estimate druggability of these pockets through machine learning. This is something also we developed, and what we are doing now is to estimate druggability a long time. That is, we track the pockets, we know which they are, and try to see which is the druggability changing a long time, which is a dynamical thing. And then if you detect a allostery or a kind of indication of it, then you have your druggable site, and then you can go for a small molecule, for instance. However, still with the same tool, you can do static pocket detection, still study your druggability or protacability, as we have seen before, and then maybe you go for something like a prota, because even if it's not allosteric, then maybe you can try to degrade it. So, I mean, if you don't find allostery, it's not just, you cannot do anything on these hotspots which are good for selectivity. So in conclusion, allostery is a complex phenomenon. Okay, so mathematically is not that trivial, and the reason is that when you try to understand it, you can have different correlation measures. So we have independence based on probabilistic independence, like the muted information. You have linear correlations, or many forms of correlation, local fluctuation correlations. So there are many possibilities. And possibly, if you use several tools together, by putting them together, you can get really a full round treatment of the thing. Pocketron idea is based on the assumption that local flexibility can tell you part of the story, probably not everything, but at least can tell you part of the story. And then when you put together things like Pocketron, molecular dynamics, and drivability via machine learning, then actually you have kind of, let's say, an enabling technology for your drug discovery activity. And obviously, this is something that you do alone. So I have many people to thank. Marco here in the audience, Walter, and Professor Andrea Cavalli, and several other colleagues. And also, I thank Franklin, which is our HPC infrastructure, and thank you to you for the very kind affection.
Thank you, Sergio. We have one question from Marco.
I don't quite understand the rationale. So what do you think the information should be transferred to cavities, lines?
Yes.
So what can you elaborate on it? So why?
Yeah.
Why is it like that?
If you have pockets which they kind of, let me say, feel isolated to each other, then possibly you can do an harmonic analysis to try to detect this kind of allostery. But the hypothesis behind Pocketron is that if they share residue, and this residue first characterize one pocket, second characterize the other pockets, the hypothesis that we did is that if this happens, this means that these two pockets kind of communicate. This is, I mean, a definition that we gave. And then we have actually check if this definition, and then when you compute this network, let's say, because you have this communication, you count them literally to see if this was matching non-allosteric phenomena. So it started from an hypothesis, from the local flexibility.
The reason for the hypothesis.
The reason for the hypothesis is that you have a local flexibility behavior, which could be an indication of the fact that these two pockets, they want to be isolated to each other. They share the residues, because first from one, let's say the coverage of one pocket, and then the same residues can be part of another pocket.
All right. Let's thank Sergio again for his